Hello, so welcome to this lesson that we've been taking on linear transformation, and here I'm going to I'm going to show you how to apply those two theorems that we did. We went through the proofs to write the range of the linear transformation and the nullity, or the null space, or the null space of linear transformation straight away without you going through a lot of stress. Okay, and also we'll find the dimension of the range of T and the dimension of the nullity, or the nullity of T. The nullity of T is the dimension of the null space of T. Okay, and we'll verify that the nullity of T plus the dimension of T is equal to the dimension of the main vector V. So what does this V here means? This V here, then write it. This is V, and mostly we have a transformation that takes V to W. That is what we wanted to show, right? So we'll come back to a theorem that talks about this whole dimension called the rank-nullity theorem. I'll take my time to go through that in a separate video, but for this one, we'll verify that before we go to that theorem. Okay. So now we have a transformation to define by T such that we take a polynomial of degree 2 in R and maps to a 2 by 2 square matrix in R. So, and it's defined by T of f of x, and this f of x is a polynomial of degree 2, should give me f of 1 minus f of 2 as my first matrix entry, and 0, 0, and then f of 0 here. Okay, so this is an example of the vector or linear transformation where the range of T would not be the same thing as what we have here. In our last one of the examples that we solved, so remember this is V and this is W, right? So that's what we are used to, that T of V, T such that V maps to W, and here V is specifically the polynomial of degree 2, and then W is 2 by 2 square matrix, right? So if you remember, in our previous lesson, we said that the range of T is equal to the span of T of some beta here, right, which is equal to the span of T of 1. Oh, sorry, I didn't say T of 1, right? T of V1, T of V2, all the way to T of Vn, where beta is equal to V1, V2, Vn is the basis for V. In other words, here, let me write this V here. Let me be specific for the P2 of R, right? So the beta is a basis for the V, and here the V is polynomial degree 2. What is the basis for this polynomial here? That means beta is equal to what? For a polynomial of degree 2, it can be spun, or the basis is 1, x and x squared, right? Every polynomial you have in a polynomial of degree 2 will be spun by these things. Every polynomial of degree 2 will be spun by this. So you have you can have the polynomial. So if I give an example of polynomial of degree 2 to be, let's say, 1 plus x squared, this is a linear combination of this and that. Okay, you can have 2 minus 3x, and that is the linear combination of 1 and then x, because you have 2 times 1 plus negative 3 times x, right? So that's what I mean. I mean that the basis for a polynomial of degree 2 is 1, x, and x squared. Okay, now let's see. So it means that the range of T, what is it equal to? It's equal to the span of T of 1, T of x, and then T of x squared. That's what the whole thing is saying, right? Because that was a theorem that we had. So the range of T is equal to the span of these things. Now, what is T of 1? T of 1 is equal to what? What is 1? 1 is a polynomial, and 1 can be written as, in terms of polynomial, 1 is equal to, polynomial of degree 2 is 1 plus 0x plus 0x squared, right? This is a polynomial of degree 2. And so 1 is the f of x. Here our f of x is equal to 1. So what is t of 1? T of 1 is going to be f of 1. So when f of x is equal to just 1, so what I'm trying to say here is t of f of x. Here f of x is equal to 1. So what is f of 1? I have my f of x to just be a constant. F of 1, f of x is just the constant 1. In this particular problem, f of x is equal to 1, right? What is f of 1? So here the transformation is saying we should find f of 1. It's a constant function, so you still have 1 minus, what is f of 2? Right, f of 2 is 1 because it's still a constant function, and 0, 0. What is f of 0? It's still 1 because it's a constant function, because we don't have any x here to put 0 there, right? So for a constant function, f of whatever you get is still the constant, and this will give me 0, 0, 0, 1, right? So I have that. Now what is t of x? Here for t of x, f of x is equal to what? F of x will be equal to x, right? So for t of x, f of x is equal to x. So let me just write it well. So what is f of 1? For f of x equals 1, x, f of 1 is 1, so you put in 1 here, minus f of 2, which is 2, and 0, 0, f of 0, that is 0. And this is going to give me negative 1, 0, 0, 0. Right? What is the other one I need is t of x squared. Right? And for t of x squared, f of x is equal to what? For t of x squared, f of x is equal to x squared. Now what is f of 1? F of 1 is 1, f of 2 is negative, so minus, f of 2 is 4, because you're going to put 2 here and then you square it. And 0, 0, f of 0 is still 0, right? And this is going to give me negative 3, 0, 0, 0. Now let me go ahead. So it means that my range of t is equal to a span of the t of these things that we got. Okay, it's going to be the span of the set t of 1, t of x, t, and t of 1 gave us this, t of s gave us that, and t of x squared gave us that. So you're going to have the span of the set 0, 0, 0, 1. This is a vector in that. Negative 1 is 0, 0, 0. Negative 3, 0, 0, 0. But if you look at it very carefully, realize that this guy and this guy are the same, like they are similar. Notice that negative 3, 0, 0, 0 is actually equal to 3 into negative 1, 0, 0, 0. Right, so it means this guy, this last one, is a scalar multiple of this one. So we can drop this one, the last one, and say that r of t, because it will give us duplication, because the same things happen. R of t is equal to the span of 0, 0, 0, 1 and then negative 1, 0, 0, 0. So this set forms the basis of r of t. So every element or every value you get in the range of t, or all the transformed vectors, can be expressed as a linear combination of these two things. Okay, now what can we say? On the other hand, the problem says we should find the dimension of r of t. So how many vectors do you have in this set? We have 2, so the dimension is just 2. Okay, so now let's go to finding the nullity of t and then its dimension as well. Remember, the t of f of x is defined to be f of 1 minus f of 2, 0, 0, f of 0, right? And the nullity of t is defined as what? What is the general form of a polynomial of degree 2? So we have t such that t picks a polynomial of degree 2, sorry, . and maps to a 2 by 2 square matrix, right? So it means f of x generally for polynomial of degree 2 is a plus bx plus cx squared. That is a general form of a polynomial of degree 2. So we want to find f of 1, right? We want to make sure that we want to find all the polynomials of the form this, right, such that the t of that f of x will give you the 0 vector in w. Here w is this and this is v. So, okay, and the 0 vector in w is 0 0 0 0. That's a 0 matrix. Okay, so we want to find all this form such that the transformation will give you the 0. So we'll have to first find t of f of s, the general one, and equate it to 0. So what is f of 1? To get t of f of s, I need to find f of 1 and put it here, right? F of 1 in terms of this f is going to be a plus b plus c. Now what is f of 2? F of 2 is going to be equal to a plus 2b plus 4c, right? That's what we have. What is f of 0? Is equal to a, right? So it means t of this f that I have is going to be f of 1 minus f of 2. So let's do that here. F of 1 minus f of 2. That will be what? This whole thing minus this whole thing. A minus a is going to be 0. So I wouldn't write that. So this a minus that a, I have 0. B minus 2b, I'm going to have negative b. C minus 4c, I'm going to have negative 3c. So I have that. So f of 1 minus f of b, f of 2 is going to give a negative b minus 3c, right? We have negative b minus 3c, and on the other hand, I'm going to have let's see, I'm going to have 0 here and 0 here, and f of 0 gave us a, right? And this should give me 0 0 0, right? So when I transform the general vector in polynomial of degree 2, this is what I have. This is a general transformation, and I should get the the 0 matrix. If you have two matrices that are equal, what does it mean? It means that here I'm going to equate coefficient or same side. So it means that a is equal to 0 because this side and that side should be the same. And then the other hand is that minus b minus 3c should be equal to 0. So it means b or negative b should be equal to 3c. So b should be equal to negative 3c, right? So a is 0. So all the general polynomial of degree 2 that will give us this 0 transformation should be f of x equals what? A is what? 0. We had a to be 0, so I'm not going to write it here. Is 0. B is negative 3cx, and then what is c? C is still c. So this is going to be equal to c out negative 3x plus x squared. So any scalar multiple of this kind of polynomial of degree 2, when you transform it, you get 0. That's what it means. You can actually pick when c is 1. When c is 1, what is going to happen? We know a is 0, so we're going to have c is 1, so I'm going to have what again? Let's see. B is equal to negative 3c. Yeah, so b is negative 3c, so I'm going to have negative 3 into when c is 1 because b is negative 3c. There's a negative in front of it already. So I'm going to plug them here. So what we have here is that b is negative 3c, so I'm going to have negative 3c. So we're going to 3c minus 3c 0 0 a is 0. So I mean when you plug this thing back, we're going to have 0 0 0, right? But what it means is that when you pick c is equal to 1 and you find f of 1 whatever and plug them here, you get 0. That's what the whole thing means, right? So we've been able to find a general second degree polynomial of this form, c into negative 3 x plus x squared, such that this scalar multiple of the scalar any scalar multiple of negative 3x plus x squared, when you transform it, you're going to get the zero matrix. So it means the null space of T here, this null space of T is equal to the span, right, is equal to the span of, this vector negative 3x plus x squared. Just as, so what is the dimension of this? So it means the basis, the basis for the null space of T is equal to the set negative 3x plus x squared. So what is the dimension of the null space of T, which we can call it nullity of T, is equal to, how many vectors do you have in this set? It's just one. Remember, this is plus, this is not comma. If it was a comma, then you have two things. So we have one. Now we're supposed to verify that, the second part was to verify that the summation, the nullity of T, which gave us 1, plus the dimension of the range of T, which gave us 2, is equal to the dimension of V. This gave us 3, right? So this will give us 3. And V here is the polynomial of degree 2. What is the basis of that? We said the basis for such polynomial of degree 2 is 1 x comma x squared. What is the dimension here? The dimension of this B is equal to 3. And yeah, this is 3. So this verification is being achieved, right? So these are some of the things we've come to understand and realize in linear transformation. In our next lessons, we're going to talk more about the rank-nullity theorem, which we'll use it to also write some proofs in linear algebra. Stay tuned and don't forget to subscribe to my channel if you have not subscribed. See you next time.